Okay, so last time we talked about types of reactions, and we also talked about redox reactions, how to balance them in acidic and basic solutions. So we're going to move on here to a little bit of potpourri of a few chapters kind of mixed together. In this chapter are these sort of lectures here. We're going to talk about really stoichiometry. We're also going to talk about molarity and concentration, and we will also get into titrations, as that is a big experiment coming up on Thursday. I think we're going to start it and stuff like that. So previously we talked about balancing equations and obviously calculating grams to moles. So when we do stoichiometry, it involves really using an equation to answer a number of questions. We want to basically figure out, maybe how much product we would produce if we did a reaction. We also might want to figure out, if we know how much product we produced, how much reactants we started with. We could also, if we know, for example, one reactant, we could use stoichiometry to figure out how much of the other reactant we would need. And also, if we know one product that's made, we could also use stoichiometry to figure out how much of the other product is made. So stoichiometry really involves using a balanced equation. So if we have an equation such as this here, balance it here. So if we have this balanced equation, we can look at the coefficients and we could get what is referred to as the mole to mole relationship. And that is using the coefficients really as a conversion factor. So sometimes people freak out about stoichiometry, think it's like super hard, but it really is just a conversion factor. And the idea here is, instead of sort of looking up the conversion factor in a table, we actually go to the equation to get the conversion factor. And that is, again, because typically in stoichiometry problems, we are given a piece of information about somebody in the equation, but we're actually interested in somebody else. So we need a way to kind of go from, say, a reactant to a reactant, or a reactant to a product, or vice versa. So from this one equation, we could come up with a number of relationships. We could say that for every 3 moles of H2 we toss in there, we will get 1 mole of N2. And again, that is just the coefficients is where we're getting these numbers. As we'll talk about, obviously, when you do these type of problems, that is always really the first thing that you want to do, is make sure you have a balanced equation, because if you don't have the right balanced equations, you have the wrong coefficients, and then you have the wrong relationships, and your whole calculation is going to be incorrect. We could also say that for every 3 moles of H2 we toss in there, we will get out 2 moles of NH3. And we could also say for every 1 mole of N2 we put in there, we get out 2 moles of NH3. So these are the 3 what are referred to as stoichiometric equivalents or equalities that you get from this equation. They clearly are not equal to each other in terms of numbers. 3 doesn't equal 1, I think, but they are equal to each other in terms of like proportions. You need to kind of toss in there to make this reaction to sort of go. So since these are really equalities, like any type of equalities, you could basically write 2 conversion factors for each equality that you have. For example, for our first one here, we could say for every 3 moles of H2 up on top, we get 1 mole of N2 on the bottom. We could also flip it around the other way. 1 mole of N2 on top, 3 moles of H2 on the bottom. For our second one here, we could have 3 moles of H2 up on top, 2 moles of NH3 on the bottom, or 2 moles of NH3 on top, and 3 moles of H2 on the bottom. And lastly here, we can go with 1 mole of N2 up on top, 2 moles of NH3, or 2 moles of NH3 gives us 1 mole of N2. So from this one equation, we have 3 equalities and basically 6 conversion factors that you could use in a calculation. Will you use all 6 in the calculation? The answer is no, unless you're doing something superly wrong, badly wrong. You will really just use whichever one you need. So usually just use one, but they are all basically available to you in an equation. So for example, if we were going to do, say, something like this, let's just say, for example, here, when we look at problems, there's really kind of 4 basic steps to follow if you're doing a basic stoichiometry problem. What makes something sort of a basic stoichiometry problem is you're really just given one piece of information about somebody in the equation. It could be a product, could be a reactant, but you just really have one piece of information. So let's just say that we produced, in this case, 32.5 grams of NH3. We want to know how many grams of, we'll do H2 we started with. So all basic stoichiometry problems pretty much follow the same 4 steps. And if you do those 4 steps in order, don't skip a step unless it's already done for you. Don't go backwards. You should end up in the right sort of area. So what is the sort of 4 steps? The first step is you should always start with a balanced equation. So if the equation is given to you, you want to definitely make sure that it is balanced. If the equation is given to you in words, you want to make sure, again, that you start with the right formulas and then balance it, not try to do it all at once. Once you have it balanced, pretty much the next thing that you're going to do is take whatever they gave you, basically, and you're going to convert it to moles, which usually means whatever unit they give it to you in, you pretty much need to get it to grams. And remember that our conversion factor from grams to moles is the molar mass from the periodic table. So in this case, we would need to go to the periodic table and look up the molar mass there for NH3, and that is 1 nitrogen at 1401. That is 3 hydrogens at 1.008 each. And that will give us our molar mass here for our NH3. That's going to give us 1703 grams per mole. So pretty much your second step that you're going to do is take what they gave you, which pretty much this is the only thing that was given to us. And we're going to go 32.5 grams of NH3. We're going to use the molar mass from the periodic table to convert them into moles. And we're going to put the grams on the bottom, 1703 grams per mole of NH3. Now, you don't necessarily have to get an answer at this point, but I will, since we're going to look at it sort of in steps here. So I'm going to take the 32.5 divided by 1703, going to give me a, and I'm not going to round too much here, 1.9084 moles of NH3. So first step in a basic stoichiometry problem, make sure you have a balanced equation. Second step is take whatever they give you in whatever units, get it to grams, and then use the molar mass from the periodic table to get it to moles. Now, the reason why we do need to do the second step and get it into moles is stoichiometry is based off of the mole to mole relationship. So we need everybody in the proper units so everything cancels. Now we come to the third step in a basic stoichiometry problem, which is the big stoichiometry move. We're going to go to the balanced equation. We're going to find the 2 things we're interested in. Obviously, one thing we're interested in is what it gave us, which was the NH3. The other thing we're interested in is what we're trying to find, which in this case is H2. So that's going to give us, again, from the equation, really a conversion factor that's going to allow us to move from our product side over to our reactant side. Again, can't look up on a table, how many moles is there in H2 to NH3, right? So we use the equation basically as a conversion factor. That is the middle one here, basically. So that is the relationship that we could get from the equation. That's going to give us, once again, our 2 options here, either this conversion factor or that conversion factor that we need to use. And it's just like a regular conversion factor, opposites cancel. So we want to get rid of NH3 and we want to end up at H2. So that we need the NH3 on the bottom, which would be this guy right here, would be the proper conversion factor that we need to use. So that would be our third step. We would take our number that we had there. Actually, I'll do it up here so you can see it maybe a little better. We're going to use, for our third step here, our mole to mole relationship from the equation. We got 2 moles of NH3 gives us 3 moles of H2. That is the big stoichiometry move right there. That little conversion factor that takes us from NH3 in this example to H2. And basically, we're going to multiply by 3 and divide by 2. And again, I'm not going to round too much. We'll get a 2.8626 moles of H2. Now, if I were looking for just moles of H2, I would be done. I could put a box around it. But very commonly, you typically want some other unit. So the fourth step, so I'll just change that to a 4. The fourth step in this case is we will actually a lot of times take those moles and convert it to some other unit. In this case, we're looking for grams. So we do need to go back to the periodic table. We also have to remember that we're no longer at NH3, right? So we are now at H2. So we got to get the molar mass for H2. So that's going to go to our periodic table, H2, 2 times 1.008 grams per mole. Going to get us something like a 2.016 grams per mole. So that will be our last step here, 2.8626 moles of H2 using our molar mass as our conversion factor, 2.016 grams per mole. Gonna tell us here that looks like at this point we could kind of round it, maybe 5.77 grams of H2 would have been needed in this case. So all basic stoichiometry problems are pretty much these 4 steps: balance the equation, convert to moles, do the mole to mole relationship from the equation, and then take those moles to some other unit, again, very commonly grams at the end, using the molar mass. Now, clearly, I did it in steps as separate calculations. I didn't round too much, but if you wanted to, you could roll from one calculation, to the next, and to your answer, and not get answers, obviously, in the middle. If you do get answers, not a big deal. Just again, don't round too much until you get to the very end. Any questions on that there? So as we just saw there, these are our basic steps that we want to use in a stoichiometry problem. And we really could use these type of calculations really to find out anything in an equation. Like I said, if you know how much products you produce, like we just did, you can figure out how much reactants. If you know how much reactants, you can figure out how much products. And something that sometimes people misunderstand as well is they always sometimes think that you do have to kind of go across the arrow to do the relationship. You don't. You could do stoichiometry between 2 reactants. You could do stoichiometry between 2 products. You could also go, obviously, reactant to product or product to reactant. So you don't necessarily always have to kind of go across the arrow there to do the relationship. You could stay on the same side and do it. But again, those are really your basic ones. Balance equation. Remember that pretty much none of this works correctly if you don't have a balance equation. Again, convert things to moles, use the mole-to-mole relationship, and then obviously look for what you are trying to find. So let's say we had something like this. Let's say we had this equation here. We took a little sodium iodide, reacted with some lead nitrate. Gives us a little lead 2 iodide and a little sodium nitrate here, right? So let's say that we, in this case, actually produced. Go with we produced 10.6 grams of PbI2. How many grams of NaI did we start with? And how many grams of NaNO3 was also produced? All right, so take a few moments there, follow those steps. I'll give you some numbers here. Sodium is 2299. We have iodide there, which is 126.9. Lead, 207.2. We got nitrogen, I think. Nitrogen, 1401. Oxygen, 16. I got everybody, I think. All right, so looking for two answers there. See what you come up with here. I'll do it as well since I made it up. Let's see what... Okay, so let's take a look, see how you're doing. Basically, we're starting with 10.6 grams of this guy. We want to know two things. We want to know basically how much reactant we would start with, and we also want to know basically how much product we would also produce. It doesn't really matter which one you go after first. You can do either one. I'm going to go after this one first, and then I'll do this one second. We're going to follow the same four steps. So this is a basic stoichiometry problem. We're just given one piece of information, and we're looking for other information about things in the equation. So first thing we want to do is balance the equation, and in this case, it is not balanced. So I think we need a 2 there, and I think we need a 2 there, and now we should be balanced. Remember, you always want to make sure that you balance it. Otherwise, again, you will not have the right coefficients and the wrong relationships. Now that we have that, this is really the only thing that we have given to us, which is 10.6 grams. We do need to convert that into moles. So we're going to convert our PbI2 into moles. So we'll need the molar mass from the periodic table. It looks like we got a 207.2 grams per mole for the lead, a couple 126.9 for our iodides, and that's going to give us, I want to say 441. Sounds like a right number. 126.9 plus a 207.2, 461, pretty close, 461 grams per mole. So second step is take what they gave us, which is 10.6 grams of PbI2. We're going to use the molar mass from the periodic table to convert that into moles. So we really could use our stoichiometry relationship there, or our mole-to-mole relationship. And if we do that, again, if you get a number at this point, don't round too much, but you'll get something like 0.02299 moles of PbI2. So now I'm going to do to the sodium iodide, which is my third relationship there. We're going to actually do the stoichiometry, the mole-to-mole relationship here. Obviously, here we're converting to moles. So when we look at the equation, we want to find the two things we're interested in this case, which is not a highlighter, that is a pen. Let's try that one. We have this guy and this guy. And from the equation, which are just the coefficients, we can see it's a 2 mole to 1 mole relationship. So for every 2 moles of NaI I put in there, I get 1 mole of PbI2. That again is going to be really our conversion factor to get us over to NaI. So if I do that there, I'll take my number from above, 0.02299 moles of PbI2. Opposites canceling, so we're going to go with 1 mole PbI2 on the bottom 2 moles of NaI up on top. The moles of the PbI2 will cancel. We're basically going to multiply it by 2. Can give us 0.4, missed a 0 there, 0.04599 moles of NaI. We are looking for how many grams, which means the fourth step is we're going to convert these moles into grams. And again, to do that, we will need the molar mass of NaI. That's going to be 2299 and 126.9 grams per mole. That's going to get us there 2299 plus 126.9, about 149.9. We're going to use that as our conversion factor here. We want that on top, so 149.9 grams per mole of NaI. And that moles will cancel. And that would get us here roughly about 6.89 grams of NaI here. And again, this would be our fourth step. Any questions on any of those steps for that one there? Yeah. When you do the molar mass? No. So you only, when you do the molar mass from the periodic table, it should be based just on the formula. Because if you use it there and then use it again, you overused it. So that is what molar mass is. It's how many grams there are per 1 mole, which means basically you just take the formula by itself always when you do molar mass, regardless of what the coefficient may be in the balance equation. The only place you really will use the coefficient in a calculation is in this type of calculation, in the stoichiometry part, to show from one thing to the next. But you should never use coefficient for molar mass. It should just be based on the formula. Yep. Other questions? All right, there was a second part to this, which was in addition to figuring out how much sodium iodide we were looking for, we also wanted to figure out how much sodium nitrate we would produce. So really, we would do the same steps, which is balance the equation, which we already did, convert to moles, which we already did. At this point, though, we just now vary here off of our third step. So we could take this number here, and now we could look at the equation and find the relationship between our lead 2 iodide and our sodium nitrate. So that's going to give us our other relationship. And from that relationship and the equation there, we could see that for every, and we'll basically be picking up on step number 3 here, for every 1 mole of PbI2, you get 2 moles of NaNO3. So it's a basically 1 to 2 relationship. So taking our moles that we had here, we'll go 0.02299 moles of PbI2 using the relationship from the equation, 2 moles of NaNO3 up on top, 1 mole of the PbI2 on the bottom. They will cancel. We're going to multiply that number by 2 again and basically end up with 0.04599 moles of sodium nitrate. Once again, here we're looking for grams, so we need to go back to the periodic table and get the molar mass of our sodium nitrate, which is 2299 for the sodium, plus 1401 there for our nitrogen, plus 3 times 16 for our oxygens. So if we do all that good stuff there, 2299 plus 1401 plus 3 times our 16 can give you 85 grams per mole. So our fourth step here, taking our number that we had, using the molar mass from the periodic table to figure out how many grams that would be. That was 85 grams per mole. That would get me 0.04599, roughly 3 0.91 grams of NaNO3. Since this is a product, this would also be known as the theoretical probably yield when you do that, based on what you would start with. That would be what you would end up there. So that would be our second answer here. So again, you can hopefully see our yellow road here. You can use really the relationship from anybody in the equation as long as you know just one piece of information. Yeah. Any questions on that there? All right, let's take a look at one more basic stoichiometry problem here before we get into more complicated ones. Methanol burns in air according to this equation. If you had 209 grams of methanol, which is the CH3OH, what is the mass or grams of water you would produce? So we want to know how many grams of this guy, basically, starting with this guy. Again, carbon 12.01, hydrogen 1.008, oxygen 16. All right, so let's see what you end up with here. Okay, so let's take a look. So again, it's the basic stoichiometry problem. We're really just given one piece of information about this guy. We ultimately want to get over to water, basically. So we want to follow our steps. So the first step is balance the equation, which it is. So we're good on that. Next step is take whatever they gave us and convert it into moles, which we do need to do here. So before we can convert that into moles, we will need the molar mass, right? So that's going to be for our CH3OH. So we'll have 12.01 for the carbon. There are actually 4 hydrogens, each at 1.008, and 1 oxygen there. That's going to give us a molar mass here of 3204, I think. Grams per mole. So we'll take our starting number here, 209 grams of CH3OH, using our molar mass grams on the bottom so that we end up with moles. So 3204 grams per mole here. And again, if you want to get an answer at this point, you can. You could continue on with the calculation if you want to as well. 209 divided by 3204. Not doing, again, a ton of rounding here. 6.5231 moles of CH3OH. Any questions so far? Now that we have that, we're not interested in that. And this is where we're going to go again to our equation, and we're going to look at what they gave us. We're going to look at what we're trying to find, and we're going to get that conversion factor, which is stoichiometry, to allow us to go from methanol to water in this case. So our mole to mole relationship here from the equation is for every 2 moles of CH3OH. And again, just the coefficient gives you 4 moles of our water in this case. So taking our number from the previous step there and continuing on with our calculation, we will go opposites cancel. So our methanol is going to go on the bottom. That's going to give us 2 moles of methanol on the bottom and 4 moles of water. That is the big stoichiometry move right there. And we're going to end up with, looks like about 13.046 moles of water. Now, again, if I did want moles, I could simply clean up the sig figs here and box it. But we do want grams, so we do need a 4th step, and that 4th step is to take moles, because you should always be in moles at this point. If you're not at moles at this point, you did something wrong. And in this case, we're going to go to grams. That is going to require our molar mass for water. So again, we need to go back to the periodic table and get our molar mass for water. 2 times 1.008 plus a 16 for the oxygen. Going to give us 18.02 grams per mole. So using that as a conversion factor, we'll take our 13.046 moles of water. Gonna do our moles on the bottom here and our grams up on top. And And the moles here will cancel, and that will get us 235 grams of water. This would be, again, what is referred to as the theoretical yield. The theoretical yield is your maximum amount of product you should make. It's a yield, which means it could only be a product, so it's got to be a product. If everything went perfect, so if you did this reaction, everything went perfect, if you put in there 209 grams of methanol, you ideally should get out about 235 grams of water if everything went perfect. Things don't go perfect, but we'll talk about that later. Again, here I did it in parts, but you could roll again from calculation to calculation without getting an answer in between. Any questions on basic stoichiometry problems? I would recommend the 4-step approach here for basic stoichiometry problems. It's just obviously the easiest sort of move. All right, then let us talk about a little bit more complicated, perhaps, stoichiometry problems. And those involve limiting reagents. Sometimes they're referred to as limiting reactants. So limiting reagents is the idea that whenever you do a reaction based on the stoichiometry there will always be a reactant that pretty much gets used up first. And that is what is known as your limiting reagent. So your limiting reagent is the reactant gets used up first. And there should also be a reagent there that is known as your excess reagent. And the excess reagent you have plenty of. You'll actually have some left over after the reaction. That's how much of that you have. You have so much that you have some left over when it's all said and done. So why are limiting reagents really important? If you just take a very simple example of if I had a reaction of A plus B and they come together to make A and B, if A was my limiting reagent and B was my excess reagent, at some point I'm going to run out of A as it's my limiting reagent. Once I run out of A, is there any chance that I can make any product? I would not be able to make any more product at that point because obviously here I need an A and a B to come together to make the product. And if I don't have any A, I just got a bunch of B's pretty much left over and no products being made. So it is always the limiting reagent that basically determines how much product you will make. So the limiting reagent is always the one that you should use to figure out how much product you're going to make because it is, like the name implies, the one that limits how much product you can make because as soon as it's gone, there's no chance that you're going to be able to make any products. So how do you know if it's a limiting reagent problem? There's a very simple thing to look at to know, hey, this is a limiting reagent problem. And pretty much this is what you would look for if you can get to moles of both of your reactants, or all your reactants really, it's a limiting reagent problem. So if you have enough information given to you that you can very easily convert whatever they gave you into moles of each reactant, it is a limiting reagent situation and you need to determine which one's the limiting reagent. Clearly, all the examples we just previously did, we only had one piece of information, right? So we didn't have enough information to figure out the moles of each reactant. So those are what are sort of considered basic stoichiometry problems. It's implied in those type of problems that if you have a reactant given to you and just one piece of information, that that reactant is the limiting reagent and the other guy's the excess. So it's usually implied in that situation. But if you got enough information that you pretty much could hit the moles of each reactant, then it's a limiting reagent problem. How can you do these problems? Well, frankly, there's multiple ways. So we're going to talk about 2 ways. One I like better than the other. And then we'll talk about the third most common way people are taught as well, which probably will be familiar to you. You could choose any way you like. And I'll talk about why one way maybe is beneficial than another way. So let's take a look at a problem like this, and we'll do it together, and I'll show you the two different ways, and then we'll talk about, again, the third way that's very commonly done. So in a process here, we're going to take 124 grams of aluminum, and we're going to react it with 601 grams of iron 3 oxide. And we want to know how much aluminum oxide would be produced in this case. So we'll need some information here. So aluminum there, 2698. We got oxygen at 16. We have our iron at 5585, I think there. I feel like I'm missing somebody. Aluminum, oxygen, and that's maybe everybody, I think, actually. All right. So first off, when I read this, I have grams of aluminum and I have grams of my iron 3 oxide. I definitely could get to moles. I could definitely get the moles without a lot of work. So because I could get the moles of each of my reactants, I know that this is a limiting reagent problem. So that, again, is how I could recognize that it is. So approach number one is really the same approach that we took with the basic stoichiometry problems. We're going to balance the equation. We're going to convert to moles, and really, no matter which one you do, the first two steps are always the same. And right around here, though, we're going to figure out the limiting reagent. So we're going to take a moment out from our 4 steps and sort of figure out the limiting reagent. Once we do, we're going to pick back up with the limiting reagent and do our mole to mole relationship, and then our moles to some other unit. So the first thing we want to do pretty much in any approach is have a balanced equation, which we do, so we're good. Really, the second thing that you want to do pretty much in any approach is you want to convert everybody to moles, so we'll do that. Here we will get our moles of aluminum, and we'll take our 124 grams of aluminum, use the molar mass from the periodic table of 2698 grams per mole of aluminum. That's going to give me here 124 divided by 2698. We'll go with 4.596 moles of aluminum. We're going to do the exact same type of calculation for our other reactant, and also why we know this is a limiting reagent problem, because we could get to moles. We're going to go with our 601 grams of Fe2O3. We also will go to the periodic table and calculate the molar mass. That is 2 times 5585 for the 2 irons, plus 3 times 16 for the oxygens. That's going to give us 159.7 grams per mole here of Fe2O3. So that's a 601 divided by 159.7, going to give us 3.763 moles of iron 3 oxide. Any questions so far? Now, these are really the starting moles of each of these guys that you have. So we really did this, we did this. Now that we are here, we do need to do a calculation to figure out which one's the limiting reactant. So when you do figure out which one's the limiting reagent, you do have to do a calculation basis, not just the smallest number. So it's not always the smallest number, but you do have to do some type of calculation to verify which one is the limiting reagent. So in this approach, you can do a very simple stoichiometry calculation. And what you're going to do, for example, is you could choose either reactant that you have. And basically what you want to know is, for example, if I wanted to use up all my aluminum, how much iron 3 oxide is needed? So that's just a basic small little calculation between the two reactants. So to do that calculation, I would take my 4.596 moles of aluminum. I would go to my equation and find the relationship between these two, which is a 2 mole of aluminum to 1 mole of the iron 3 oxide. I would use that relationship, and I have 2 moles of aluminum from the equation, 1 mole of iron 3 oxide. And that's going to tell me that essentially I will need about 2.298 moles of iron 3 oxide is needed. This is where you take your calculation that says how much you need to compare it to how much I am starting with, right? And do I have enough? I need 2.298. I am starting with how many moles of the iron 3 oxide? 3.7, right? So I definitely have enough. So when you compare this, you actually have enough. And what that means is if you compare those two numbers, how much you need to how much you're starting with, and you have enough, that means that this guy would be your excess reagent. And by default, the other guy would be your limiting reagent. So right off the bat, that's a really quick way you can kind of determine it if you want. Any question on that calculation? Now, just to show you, and again, you don't actually have to do both of these calculations, but if you wanted to choose the other reactant and figure out it the other way, you could also have done that. So again, you could have chose to do, if I wanted to use up all of my iron 3 oxide, how much aluminum is needed. So again, you could have kind of done the other calculation to that, which would have been 3.763 moles of iron 3 oxide using the same mole to mole relationship, just flipped. 2 moles of aluminum, 1 mole of iron 3 oxide will tell you that in this case, for the aluminum, you would need, do that. You would need 7.526 moles of aluminum is needed. Once again, you would take how much aluminum is needed, come up to your starting amount, and see if you have enough. I need 7.5, but I only have 4.5, right, to start with. That is not enough. And because that is not enough, that tells us, again, this is our limiting reagent, and the other guy would be our excess reagent. So again, you don't necessarily have to do both of those calculations. You could choose either one, and it will tell you basically which one's your limiting reagent. Any questions on how you determine limiting reagent through this method here? Now, once we determine the limiting reagent, we're going to pick back up with our third step, and it's really important that you start with the starting amount of your limiting reagent to do the rest of the calculation. So I'm going to do it on the next page. I think we'll take our, what we got there, 4.596. So we're going to take our limiting reagent now, which is our 4.596 moles of aluminum. And now we could do the rest of our calculation like we did before. We're going to go from aluminum now to our product, and it is a 2 mole to 1 mole relationship here. So from the equation, it's 2 moles of aluminum gives you 1 mole of the aluminum oxide. So we'll take our 4.596 moles of aluminum, and using our relationship from the equation, 2 moles of aluminum gives me 1 mole of aluminum oxide. That's going to cancel. We're basically going to divide it by 2 here. 4.596 divided by 2, going to give us 2.298 moles of aluminum oxide. Last step is to figure out how many grams that would be. So again, we would have to go to the periodic table, grab ourselves the molar mass here. So 2 times 2698 for the aluminum, plus 3 times 16 for the oxygens from the periodic table. Going to get us there. It's like 100, we'll call it 102. Why not? 102, I guess, grams per mole. So last step here is 2.298 moles of aluminum oxide times the molar mass from the periodic table for aluminum oxide. Gonna yield us here 2.298. About 234 grams of aluminum oxide would be produced. This again would be our theoretical yield. Question on that there. So this approach is pretty much identical to basic stoichiometry approach. You just take a little shortcut there or stop over halfway through, do your little stoichiometry or limiting reagent calculation, and then continue on with the limiting reagent. Now, in these type of problems, there's also other questions that are very commonly asked. And a very common question that's asked is, for example, how much of your excess reagent is left over? So we could also answer that pretty simply. So we know that the iron 3 oxide is our excess reagent, and we are starting with 3.763 moles of it. We know that based off of our limiting reagent calculations, if we chose the first one, we know how much we need of it, which is 2.298. So basically, if we just subtract those two, we know we started with that number there, 3.763 moles of our iron 3 oxide. We know we needed 2.298 moles is needed of it. And if we subtract it, that will tell us how much is left over. We have approximately 1.465 moles of it left over, which we could use the molar mass, which we also have over here. So that's 159.7. And we can figure out how many grams that would be. 1.465 moles of our iron 3 oxide times the molar mass, which I remembered a minute ago, 159.7. 159.7 grams per mole. And that would tell us that we will have left over in grams approximately 234 grams of it left over. Remember on that one, we started with 601 grams. Yeah, so we started with 601 grams of it. We'll have about 234 grams left over. So, you know, we used just under 400 grams of it in this reaction. Any questions on this approach? Now, if you did your limiting reagent calculation and you chose to do this calculation and you were asked that question, you would need to go back and do this calculation to figure that answer out. So again, you might choose correctly if you had asked that question, or you may not have chose correctly, so you might have had to go back and actually do that. Any question on this approach? A common approach similar to this, probably taught by most people, is you do two separate stoichiometry calculations, one with the 124 grams of aluminum and figure out how many grams of your product you would produce. And then you do a separate calculation with the 601 grams of the iron 3 oxide and figure out how much aluminum oxide it would produce. Whichever one produces the smaller amount is both your limiting reagent and your theoretical yield, which is how a lot of people are taught these days to kind of do these type of problems. So that's, again, another approach, works perfectly the same. You get the same answers. If you like that approach, you can still do that approach. I don't really care. So what I'm going to now show you is a third approach, which is sometimes in a limiting reagent problem, a really beneficial sort of approach to do, because very quickly you can pretty much answer any question that might be asked of you if you're doing these type of problems. Second benefit of this calculation is if you're going to go take 200B, it's pretty much similar, very similar to the calculation you do in 200B for the most of the day there in 200B. So it's helpful there as well. So we're going to actually just pick it up here with the same two first steps. It's balance the equation, it's converting to moles. And the next thing we're going to do is we're going to actually do what is referred to as an ice table. And an ice table stands for initial, change, and in here, we'll call it end. When you get to 200B, it's equilibrium at that point when you go to 200B. But here, we'll just call it the end. And the idea here in the ice table approach is we want to figure out the change, and that will allow us to figure out basically how much of everybody you'll have. So to do this, you will take the balance equation, which is our aluminum and our iron 3. So we'll take our aluminum plus our iron 3 oxide, making our aluminum oxide and our iron there, I think. And here, that's a 2 and a 2, I think. 2 there and a 2 there. Now, to do this, like I said before, you balance the equation, you convert everybody to moles. And now we're going to do our ice table. So initially, we have our moles of aluminum. And again, I'm just going to steal what we calculated earlier. That was 4.596. So that's going to be 4.596 moles. We also have our moles of our iron 3 oxide, which was 3.763. 3.763 moles. So again, it's very similar to all the other approaches, balance equation, convert to moles. Now we're going to do the ice table. That is the only piece of information that we have, so it's very safe to assume we have 0 of each of these guys, yeah, to start with. Now, the change part is usually represented by a letter, and that letter is X, is usually what represents the change part. When this reaction takes place, my reactants, should I have more or less reactants as the reaction takes place? In order to make products, you need reactants, right? Which means the amount of reactants should decrease, the amount of products should actually increase. And the way we represent that in an ice table is anything that's decreasing gets a minus, and anything that's sort of increasing gets a plus sign. And we use X to represent that change. So when we get to the change part here of this table, this is going to be minus 2x, and the 2 comes from the coefficient. And it's really important that you put the coefficient in there, because what that's going to do for you is your mole-to-mole relationship all wrapped up in one. Yeah. So if you don't put the coefficient, you won't be doing the mole-to-mole relationship, and you'll get the wrong answer. So it's really important to do that. Obviously here, this is going to be minus x, since the coefficient here is 1, basically. Yeah. Coming to the other side, this will be plus x, because the coefficient here is 1. And this would be plus 2x, because the coefficient here is 2. So again, it's really important in the change part that you include the coefficient. Otherwise, you will not have the correct, like I said, mole-to-mole relationship. What we're going to basically do now is just bring everybody down. And this is going to be 4.596 moles minus 2x. Just going to kind of get rid of the mole part here to make it not so crowded. 3.763 minus x, x and 2x. Yeah. All right. Any questions on sort of the ice table part here? So we still need to determine which one is our limiting reagent. So to do that, what we're going to do is take each of our reactants and basically set it equal to 0 and solve for x. So basically, this is going to give me 2x is equal to 4.596. Basically, x, we're going to divide the 2, and fairly quickly we can determine that we have a 2.298, and these are moles. If I set this guy equal to 0, just bring the x to the other side. X is equal to, in this case, 3.763 moles. In this case, we're looking for the smallest number. Which one's the smallest number? That would be this one. The smallest moles, when you do this, is your limiting reagent. So that again means, as we saw earlier, our aluminum's our limiting reagent, and our iron 3 oxide is our excess reagent. Any questions on that? So at this point, Since this is not the smallest, we really don't need that number, okay? So why is this kind of good? Because now if we look at our sort of ice table, we now have an x value, and that x value is this x, this x, this x, and this x. It's all those x's, which means we can very quickly, for example, figure out what was asked in the question, which is, how many moles, for example, of our aluminum oxide, which if we look at our ice table is equal to x, and we know x equals 2.298 moles of aluminum oxide. We could use our molar mass that we could calculate from the periodic table like we did previously, which was 102. We times it by 102 grams per mole. And now we have our answer, right? Which is our 102. 234 grams of aluminum oxide. We also know very quickly, if I wanted to know how much of the other product I produced, I could see that the moles of iron based on the end line is 2x. So I take 2 times my value of x will give me 2 times 2.298, 4.596 moles of iron. I can use the molar mass of iron from the periodic table, which is 5585 grams per mole. I now know that I will also produce 257 grams of iron in this reaction, which would be the theoretical yield of my iron. And lastly, the question that you're sometimes asked, which is how much of your excess reagents left over? I know my excess reagent at equilibrium is equal to 3.763 moles minus X, which means 3.763 moles minus my X value of 2.298 moles gives me my 3.763 minus 2.298, 1.465 moles of my iron 3 oxide left over. Using the molar mass here, once again, of our iron 3 oxide, which we have there that we calculate up front, 159.7 grams per mole. It's going to give me my 234 grams of iron 3 oxide left over. So you could probably see here within a matter of 2 minutes, I answered pretty much any question that could be asked of you. How much of the other product, how much of the product I was looking for, how much of the excess reagent is left over, without having to necessarily go back and restart the calculation and stuff like that. Clearly, ideally, right, if we throw our X value back into our limiting reagent, we should hit 0, right? Because it's the limiting reagent, it should be used up basically in that case. So the benefit of this sort of ice table approach when you're doing limiting reagent problems, which is pretty much the only time you should probably use it. If it's a basic stoichiometry problem, you should just do the 4 steps like we talked about. But if you want to do this, the benefit of this is very quickly get pretty much answer any question that's going to be asked of you in a matter probably of minutes. You'll be able to get that without having to go back and figure out, okay, what do I need to do to figure out, my excess reagent and what calculation. And maybe less room for error as well. So those are 3 different ways that you could do limiting reagent problems. Like we did originally there, basic 4 steps with the middle calculation. You could do, like most of you are probably taught, just 2 separate calculations to figure out how much product, or you could do the ice table approach. And again, that will allow you to do a number of quick calculations. Any questions on any of those approaches? Again, I don't care which one you choose. You got to choose a legit one, though. Yeah, you can't just make up one yourself, whichever one you're comfortable doing. Any questions? All right, we're going to lay it up here for